Okay, so it's about time for us to get started. On Brightspace, I posted some information about the midterm. I don't know if people saw it or not. So if you go into Brightspace, you click the link for midterm 1. There's been practice stuff up there for ages, but the top 3 files now are midterm 1 information. This is just sort of a list of, day and time, where it is, the big lab, what's covered, what's the format, and all that stuff. So that's there for your midterm information. I posted a list of topics. Some people like to just have a checklist as they study. So these are the things we've covered since we began, up to that cutoff point in lecture 15. And then along with the sheet that you can bring if you wish, I am giving you a formula sheet. This is part of the test. So this equation sheet will be provided as part of the test. So if you choose not to bring a sheet, you still have the equations you need. Any questions about the test before we go on? Just like to remind everybody, make sure you bring a calculator. There's a couple of spares in the lab, but if more than 1 or 2 people forget, you're kind of out of luck. So don't forget your calculator when you come. Okay, so any questions before we get going? No, looks like we're good. So last day we talked about, we used Gauss's law to find the electric field inside and outside of a spherical conductor and insulator. So we did lots of work last day. We got started on property 3 of our conductor, which tells us what the electric field is just outside. But we ran out of time, so we're going to pick up where we left off last time. So we started last time with a picture of our conductor. We know it has an excess charge. We know that has to sit on the surface. The first thing we established was that the electric field had to be perpendicular to the surface, because if there was a component parallel, that parallel component of electric field would make the charges move parallel to the surface. We know that's not happening because it's in static equilibrium. So that gave us the direction of the electric field. The next thing we want to find is the magnitude of the electric field. We're going to use Gauss's law to do that. So as a reminder, let's see, where can I squeeze in Gauss's law? Gauss's law says the net electric flux can be calculated as E dot A and is equal to Q enclosed divided by epsilon naught. And this bit right here means the total electric flux, or the net electric flux, all of the flux added up, so we get the total. This is a slightly new situation to us. We haven't had one of these strange surfaces before. So last time we picked our Gaussian surface, it was a cylinder that's partly inside the surface and partly outside the surface. So like if this phone is our Gaussian is our conducting surface, then my water bottle might be like the Gaussian surface. So part of it sticks out of the top, part of it is down in through the bottom. We picked a cylinder for our Gaussian surface. If we want to find the net flux through the cylinder, the net flux through the water bottle, then we have to find the net flux through 3 surfaces basically. How much flux cuts out through the top? So how many electric field lines cut through the top? How many electric field lines cut through the bottom? So how many come out through the bottom? And how many come out through the sides? So a cylinder essentially has 3 surfaces, a top, a bottom, and the tube part or the side part. To find the total flux, we find the flux through each of those faces and we add them all up. So that's where we're going with this line right here. So the total flux is through the top, the bottom, and the tube part or the side part. So our net electric flux through the top is going to be the electric field dotted with the area of the top face. The area of our top face is right here. It points out of the face. There's our area vector. We see that those 2 things are parallel. So E dot A is E times A times cosine of 0. That's because the 2 vectors are parallel. Equals E times A, and A is the area of this face. So that's the electric flux through the top face. The electric flux through our bottom face, the area vector again sticks straight out of the bottom, equals E times A. For this one, here's where we have to use the result that we know off the top of our head. What's the electric field inside a conductor? That one's 0, and we always know that's 0. So the flux through the bottom face is 0. That matches our picture. We don't see any electric field lines cutting through that bottom face. Then we also have to find the flux through the sidewall or the tube bit. So for our sidewall, the area vector sticks straight out, so kind of comes straight out like this. I'll draw that on my picture. So this area vector is straight out, parallel to the surface. The electric field is perpendicular to the surface. So E dot A is E times A. Those two things are perpendicular. The angle between them is 90 degrees. So the flux through the side walls of the cylinder is also 0. And that also matches with our diagram. We don't see any electric field lines poking out through the sides. So to find our net electric flux, it's these three added up. EA plus 0 equals EA. So our net electric flux is E times A. To use Gauss's law, we also need Q enclosed. So Q enclosed means how much charge is inside that Gaussian surface. The Gaussian surface encloses a little bit of the area of the top face. It encloses that much of the cylinder, of the conductor. That also has area A. So our Q enclosed is going to be the charge density sigma times the area of the face. Okay, so it encloses that much space. To find the total charge, we do density times area. Okay, are we good to here? That's our two sides of Gauss's law. Next we'll put it together and we'll find our expression for our electric field. So our net electric flux is Q enclosed over epsilon naught. Our net electric flux was E times A. That's equal to Q enclosed, which is sigma times A divided by epsilon naught. We've got the A on both sides of the equation, so we divide both sides by A. And we find that the electric field outside the surface of a conductor is the charge density divided by epsilon naught. And since we have a positive charge, it's perpendicular to the surface and then points out. If it were a negatively charged surface, it would be perpendicular, pointing in. Okay, any questions here before we move on?
Yes. I think it looks like it might fall out of the front if you push your monitor up there.
What do we follow on?
Like that.
This thing?
Yeah. I didn't, yeah.
Okay. I think that thing is actually kind of expensive.
Yeah.
That was one of the COVID things they put into the AV equipment. Yeah.
Did we choose sigma times area because it's a conductor?
Just because this is the density times area, and that's how you get charge. Yeah.
What if it's an insulator, so we use rho times volume?
Insulator would be tricky, right? Because we wouldn't have just the surface area charge, so we would have to think about kind of the total charge inside that cylinder. Yeah, that would be a trickier thing to do. I'm getting the problem session ready for next week. I figure you might like a little more practice with some of these Gauss's law problems. So I've got a couple of questions on that for the problem session next week. And if there seems to be call for it during the problem session, we'll just do those examples on the board or something. Yeah.
I just want to confirm, like, this kind of Gauss's law question won't be on our midterm?
No, anything we do in class. Oh wait, no, the upcoming midterm. Do you mean, like for Friday?
Yeah.
No, the cutoff was last week.
Okay.
Yeah.
So it's the more basic examples of the first example, or the one example we have of Gauss's law
Yeah,
question.
so whatever we did up to where I wrote down test cutoff, that's the sort of thing you could see. Yeah, and we won't. Yeah, we didn't cover this depth before that. This is total fair game for the next test. Okay, that takes us to the end of chapter 22, the end of our Gauss's law chapter. We're going to get started on chapter 23, which is about electric potential energy and electric potential. Okay, and some of this stuff is going to tie in with the lab that's going on this week, electric potential does. So, the chapter is called Electric Potential, but it also covers electric potential energy. So that's part of it. In fact, that's where we start with the chapter. To get started with this chapter, you do have to remember some of your basic stuff from Physics 1020 or 1050 about potential energy and the way it relates to work and kinetic energy. So a very quick review of the basics you have to know. And if you need to go back and review, this is chapters 6 and 7 out of your textbook if you want to look it over. If we want to find kinetic energy, we know the equation is a half mv squared. If you have a bunch of particles, you would do a half mv squared for each of them and add them up to get the total kinetic energy. So if we have a system of a number of I particles, the total kinetic energy K would be the sum of each individual kinetic energy, which would be the sum of each 1/2 times its mass times its speed squared. So that's how we find kinetic energy, a half mv squared. Kinetic energy, like all of the energies, those are all scalars, so energy is not a vector. When we get to potential energy, a way to define potential energy is by calling it the energy of interaction. You need some things interacting in order to get a potential energy. And an example would be gravitational potential energy. When we hold something up in the air, we can store energy. You also get spring potential energy, so we have a mass on a spring and it can store potential energy. So potential energy is energy of interaction. You can also think of it as stored energy. The change in potential energy in any system is called delta U. And we know that potential energy changes when we do work on a system. So it's negative of the work done on the system. And this work is done by internal forces. So if gravity does work on something, we get a change in the gravitational potential energy. So if something does work, we get a change in potential energy. What we're going to find in our chapter is electric potential energy. So it'll be some ways similar to other stuff, in some ways a little bit different. If we have that all of the forces acting in a system, if they're all conservative, and the best way to define a conservative force is to talk about what isn't a conservative force. An example of a non-conservative force is something like friction or air resistance, tension in a rope. So if all of the forces are conservative, which means we don't have any non-conservative forces, then we know there's a relationship between the potential energy and the force. And that relationship is that the component of force is negative of the change in potential energy as it goes through that distance. Okay? So that's the relationship between force and potential energy when the force is conservative. Okay, so force goes as negative the change in potential energy. The other thing that happens, if all the forces are conservative, it means that the total mechanical energy is conserved, where mechanical energy means potential plus kinetic. So you might have seen this in 3 different ways. So one way we write it is E final is equal to E initial plus work done by non-conservative forces. This is the way I tend to write it. This is what I'll be writing in class more often than not. You might also see the form KF plus UF equals KI plus UI. So that might be an expression you're familiar with. Final kinetic plus potential equals initial kinetic plus potential. And the last way you might have seen it would be the change in total mechanical energy is the change in kinetic plus the change in potential, and if everything is conservative, that's equal to 0. So you might have seen it in any of those 3 ways. We talked about change in potential energy is related to the work. We know that work is done by forces. We're going to be using those concepts as we go through. And we know that to calculate work done by a force, that the work is the integral of force over displacement. So that's an expression you probably saw in Physics 1050. This is how you calculate work done in general. This is force dotted with displacement. That is a scalar product, so that means F over displacement times the cosine of the angle between them, cosine theta. If you have the special case of a constant force, so if F constant, then the integral form boils down to F dot delta R. Where F dot delta R would be F times delta R times cosine theta. Maybe in Physics 1050 you introduce this concept, but you use this one in practice. So probably you saw this, but you didn't use it a whole lot. Maybe you used it for a spring, but most of the time you wouldn't use it for this. So we're going to take all of this information and we're going to apply it to electric forces to find the work done by an electric force. We use that work to figure out the change in electric potential energy due to work done by an electric force. Yep.
What is the integral, what is the variable that we're taking for the integral?
Position.
Position?
Yeah, so R stands for distance from a charge.
Okay.
Yeah. We'll get into kind of specifics of how to use this as we go. Okay, questions? Okay. So let's get going on what we're going to do here. So when we introduced electric fields, we used an analogy to gravitational fields. We're going to build our electric potential energy using the same principle. We'll look at that analogy with gravitational fields because it works more or less the same way. So if we have a mass m in a gravitational field g, it's going to feel a gravitational force m times g. This was something we talked about earlier. You can draw that force. It points straight down. Mass is positive, g is down, so the force is down. Fg equals m times g. So we know what the force is. It's m times g. We developed the idea in Physics 1050, so we'll say review 1050 notes if you need to. So by thinking about the work done by gravity, you came up with the equation for gravitational potential energy as m times g times y. Maybe mgh, that's the one that kind of pings for most people. Your book uses mgy, so I'll stick with the notation of your textbook. So mgy is your height above ground. As soon as you say height above ground, it means you need a reference point. You need to identify what you mean by ground. So in this picture here, we would call this lower point that I've shaded with gray. Typically, we're going to call that the ground. That's where y equals 0. Positive y points up. Draw that out here on the side. Our work done by the gravitational force is negative the change in potential energy. So it's minus mg times delta y. So your work is negative the change in potential energy. Change in potential energy, delta u would be m times g times delta y. Work would be the negative of that. And this would be the work done by the gravitational force. If we think about the behavior of the object related to the sign of the work done, this stuff kind of makes sense. If our object goes up, the work done is gonna be negative, so delta y will be positive, the work is negative. That makes sense, so if we take a ball, we throw it up in the air, the work done by gravity is gonna be negative, and the thing is gonna slow down. When we throw a ball up in the air, it slows down as it goes up. So this happens because delta y is up and the force is down, so delta y is opposite the direction of the force. And if your work is F times delta y times cosine theta, those two things are opposite in direction. Theta would be 180 degrees. You get F times delta y times cosine of 180, which is minus 1. So when vectors have opposite directions, the work done is negative. If we take something and we release it, it falls down. Delta y is down, the force is down. Those two things are parallel. When you find the scalar product, that would be positive. So when two vectors are in the same direction, your work done is positive. So delta y parallel to F. When the work done is positive, something speeds up. You probably talked a little while about the work kinetic energy theorem in physics 1050 that said that the work done was the change in kinetic energy. So that's kind of where these behaviors come to as well. So an important behavior, and we're going to keep coming back to this important behavior, is that if we release something from rest, it will always move towards lower potential energy. It will always move towards ground. So if you hold something up in the air and you let it go, 100% of the time it's going to fall down, because that's how objects behave. They move towards lower potential energy. So that's an important behavior that we're going to draw on as we go through this material. Okay, are we good with the recap of gravitational potential energy? Okay, so next we're going to take all of these ideas, but instead of talking about the gravitational force, we're going to talk about the electric force. So the force will be felt by a charge in an electric field. We'll probably do this one a little bit more slowly, because even though it's the same behavior, it is slightly newer material. So in our setup now, instead of having a mass in a gravitational field and feeling a gravitational force, we're going to take a positive charge. So that should maybe start getting you thinking, oh, I wonder if things are different for a negative charge. Okay, but we're going to start with a positive charge. Label that with a plus sign. It's in an electric field, which points down, and it's going to feel an electric force Q times E. The force and the field are in the same direction because the charge is positive. So this was something we talked about when we did our electric field chapter and our electric force chapter. Okay, so now let's go through the things on this side. Our electric force is charge times electric field. So this one is similar to our gravitational force. That was mg, this one is QE, so those are similar. We get the same sort of definition for electric potential energy. Gravitational potential energy was mgy. Electric potential energy is Q times E times the distance. We're going to call that distance S. So gravitational potential energy used S. We're going to use, gravitational potential energy used Y or H. For electric potential energy, we choose to use S. Okay, so for this line, this is called our electric potential energy. S is going to be our distance. So when we do gravitational potential energy equals m times g times y, we always have to refer to a ground. Basically, you're getting a coordinate system with an origin. You have to do the same thing here. You have to identify where is ground or where is S equal to 0. The common thing to do with electric fields is you call the negative plate S equals 0. So that's what you identify as your ground level. So we'll do that here. So this line is S equals 0, and positive S will go up from here. Okay, so this looks very much like the Y on our last page, but now we're choosing to use S. So then in our table, the negative plate is S equals 0. That's our ground. So S here refers to the distance from the negative plate. Now we've got our coordinate system and we've got our origin. We know that the work done by the electric force is the negative of the change in potential energy, or the negative of Q times E times delta S. So this is similar to what we said for our work done by gravitational potential energy. If we think about our behaviors, if our charge goes up towards the positive plate, our delta R would be up, our force would be down, and the work would be negative. Okay, so if it goes up towards the positive, delta R is up, force is down. Those two things are opposite. It gives a negative work done. So F is opposite from our distance, delta R. And the behavior is that it would slow down. If our charge goes down towards ground, then delta R is downwards, F is down, those two vectors would be parallel, and the work done would be positive. That's when it speeds up. This is the same behavior that we were seeing with our gravitational potential energy. If we release it from rest, so if we release this positive charge, it will naturally move to where S equals 0. So it's going to feel an electric force that pulls it down towards 0, towards the ground. And that's towards our lower electric potential energy. So let's just kind of bring this bit home, that means lower potential energy. So down here at ground level, so down here at this height, at S equals 0, the electric potential energy at this plate is the charge times the electric field times the S value, which is 0. So at the negative plate, the electric potential energy is 0. If our plates are separated by a distance d, then up here at this top plate is S equals d. And the electric potential energy up here is charge times electric field times our distance of d, which is Q times E times d. That's a positive value. So this is 0, this is positive. That makes this plate a low potential. The negative plate is low potential. And the upper plate is high potential. Potential energy. Okay, so if we release our positive charge from rest, it will move towards lower potential energy, because that's how things in the universe move. Yep?
Even once it gets to the low point, wouldn't it still feel some potential energy from the force of attraction towards, like it'll never fully be into the negative charge? Like,
Well, once it hits the plate,
we're considering it.
then it stops, right? Because it's banged into the plate. Just like you drop something and it'll stop when it hits the ground. Yep.
If the positive charge is in the middle, like let's say that S is equal to 1, so that means that delta U is negative since the work is positive, or no?
Wait, so when it moves from here to here,
No, like if it's in the middle,
it is in the middle right now,
like a little bit down.
right here. So as it moves from here to here, your potential energy is still decreasing. So delta U is negative and your work is positive as it goes from here to here. Yeah, absolutely. Okay, so this is the expression. Potential energy is Q times E times S. That's our expression for electric potential energy, kind of between the positive and negative plates here in a constant field. So this takes care of our positive charge in a constant electric field. So now you have to recognize that charge can be positive or negative, so let's try and deal with that bit next. So how do we deal with negative charges? So we'll go through all the same steps, but we'll make sure we're interpreting it the way we should. So if we have a negative charge Q, I'll label my charge as a negative. It's in an electric field. The force is Q times E, but if your charge is negative, the force and the field are opposite. So here's our electric force equals Q times E, and our charge Q is negative. Okay? So this is what we have to do when we have a negative charge. Let's go through our process. Our electric force is Q times E, that points out. So there's our electric force, we know what that is. Our electric field is Q times E times S. I've put in brackets here that it's a maximum at the negative plate. Let's make sure we understand what that means, what that's telling us. So let's put on our coordinate system again. So here's where S equals 0. There's our S pointing upwards. At this lower plate, at S equals 0, the electric potential energy is Q times E times 0 equals 0. Off the bat, it feels weird to say that 0 is the maximum. That feels strange, right? So let's look at what is the potential energy at the positive plate. So we'll still say they're separated by a distance d. So at this upper plate, this is S equals d. Our electric potential energy is U equals Q times E times d. Q is negative, E and D are both positive, so this is a negative value. So down here we have 0 joules, up here we might have minus 100 joules, and 0 is bigger than negative 100. Okay, so this indeed is still the maximum, and this is the minimum. So up here is low potential energy, and down here is high potential energy. Okay, so our behavior still works. If we take our negative charge and we release it, it will move towards the positive plate, which is low potential energy. So the behavior of the universe still checks out. We're still choosing the negative plate to be ground. We've got that in our picture. Work is minus delta U minus QE delta S. As it goes towards the positive plate, I made a typo in this line here. If you've downloaded the loads, you can scratch that bit out. If our charge goes towards the positive plate, the force is up, delta R is up, so F parallel to delta R. That gives a positive work, and it will speed up. If our charge moves down towards the negative plate, the force is up, delta R is down. So force is opposite delta R. That'll give a negative work, and it will slow down. Okay, so when we have our electric potential energy, we know that U is equal to Q times E times S. We include the sign of the charge, and S is relative to negative plate. Okay, any questions to here? Yeah?
Since we have the electric field from the positive to a negative plate, right? And negative charge attracts a positive plate, right? So that means it is in opposite direction of electric field. So does the speed of the particle gets reduced?
Yeah, as it moves from here to here, it'll speed up, right, because it's attracted to here. As it moves from here to here, it would slow down.
Yes. So the electric field doesn't interfere with the speed of the particle?
The electric field produces the force. The force describes the acceleration, which describes the speed, right? So the electric field is responsible to the force. The force is the thing that either speeds it up or slows it down.
So in this case, the work is negative.
Depends on which way it moves. If it moves up, work is positive. Moves down, work is negative. Okay, I saw your hand go up. Do you still have a question?
And what would make the charge go down?
Oh, you'd have to throw it.
Okay.
Just like to make a mass go up in the air, you have to throw it up. So yeah, that's a good question. The way to get it to go down is to throw it downwards. Yeah, good question. Okay, so let's just do a slightly conceptual recap here to make sure we got it before we move on. Because all these motions and signs can be a little bit tricky to make sure we understand. Okay, so I've got a positive charge, I've got a negative charge, I have them both in an electric field that points downwards. And then we'll go through each one of them. So part A, what is the direction of the force? We mean the electric force on each charge. Okay, so what's the direction of the electric force on the positive, up or down?
Down.
Down. So the electric force on this one points down because F is equal to Q times E. The electric force on this one is still Q times E, but Q is negative, so the force is up. There aren't quite enough words in part B. Which way does each charge move? Oh wait, it's up here. As it's released from rest. So if we let each of these go, and they're allowed to move, this one is going to move down, move with the force. This one's going to move up, moves with the force. So if they're released from rest, this one moves down, delta R. This one moves up, delta R. So which way does each charge move? We'll say with the force. Oh, now it feels like Star Trek. What is the sign of the work done on each charge by the electric field? So here we'll remember how we figure out work done. Work is equal to F dot delta R equals F delta R cosine theta. In each case, theta is 0, so in each case, work is positive. And does the electric potential energy of each charge increase or decrease? For this bit, we remember that delta U is the negative of the work done. So if work done is positive, delta U is negative. Delta U is negative. If delta U is negative, they both decrease. Yep. Repeat C. So part C is what is the sign of the work done on each charge by the electric field. So in the positive case, the force is down and delta R is down. We said it was going to move down. For the negative charge, the force is up and delta R is up. So in both cases, those two vectors are parallel. When vectors are parallel, they have a positive work done. Oh, fantastic. So we'll move on to another example. We've got 10 minutes, so I'm hopeful we're going to get it done, which is going to take us to the next step here. If potential energy is decreasing, things are speeding up because the kinetic energy is increasing and the work is positive. So we're going to do an example with some numbers to look at that behavior next. So, a proton is shot, this goes back to a question we had earlier, how do we get it to move? A proton is shot towards the positive plate. The spacing is 0.5 millimeters. So I'm going to add a few things to my picture as I go. D equals 0.500 millimeters. The proton is shut, so it starts over here at the negative plate. We're giving it some sort of initial velocity to make it go this way. Okay, so we've shot it this way. The electric field strength is 500,000 newtons per coulomb. And we see from our picture that it points towards the left. That's what the picture shows us. While we're at this, we might as well put in our coordinate system. At the negative plate is S equals 0. And towards the positive plate is our S axis. If the proton is projected from the negative plate with a speed of 2 times 10 to the 5 meters per second, so VI equals 2 times 10 to the 5 meters per second. Its initial position, it starts here at the negative plate, S initial equals 0. Does it reach the positive plate? If it does, how fast is it? If it doesn't, how close does it come? So we shoot it and want to know, does it get there? There are probably different ways to think about doing this problem. When I think about it, if I throw a ball up in the air and I want to know, will it reach the ceiling if I know the initial speed? I might say, okay, well, I know the ceiling is 3 meters high. Why don't I calculate how far up the ball can go? If it gets up to 3 meters, yes, it hits it. If it's less than 3 meters, it won't hit. More than 3 meters, it will hit. Okay, so let's use that sort of an idea. Let's say that we know the initial velocity. Let's figure out where it stops. If it stops before 0.5, it doesn't reach. If it stops at 0.5 or bigger, it will reach. So we'll ask the question, where does it stop? Because that will let us draw our conclusion. If it stops, that means the final velocity is equal to 0, and we're trying to find that final position. So we okay with the strategy? Okay. This problem, if you ask, could you do this with kinematics? I'm going to say yes, you absolutely could do this with kinematics. It could absolutely work. You know the field, you could find the force. From the force, you could find the acceleration. From the acceleration, the initial and final speeds, you could find the distance. That would be legitimate, but we're doing an energy chapter, so let's use energy methods. Okay, so we're going to try the energy approach. In our energy approach, we'll start by writing down the equation for conservation of energy. So final mechanical energy is the initial mechanical energy plus work done by non-conservative forces. We don't have anything like friction or air resistance that we're going to worry about, so we'll call this bit 0. Our final energy means our final kinetic plus our final electric potential. And that's equal to our initial energy, which is initial kinetic plus initial electric potential. Okay, so there's our expression for conservation of energy. Maybe I'll just list these off on the side, because I think this is going to get cramped. So my K final, my final kinetic energy, is 1/2 times m times v final squared. That's equal to 0, because we said it's going to come to a stop. My final electric potential energy is going to be my charge times my electric field times my final position. Final position is what I'm trying to find, so I don't know what this is. My initial kinetic energy is 1/2 times m times v initial squared. Vi I know, m I know, because it's a proton, that's something we know the mass of. And UE initial is Q times E times S initial. It starts at the negative plate, so it's Q times E times 0 equals 0. So 2 of these things are 0, the final kinetic and the initial potential. That simplifies our equation a little bit. So Q times E times SF equals 1/2 times m times the initial squared. our final position is 1/2 times m times vi squared divided by q times e. This is our mass. The initial is 2 times 10 to the 5. Charge is the charge on a proton, that's here in our table. E is the magnitude of the electric field, 500,000 newtons per coulomb. Put all those numbers in the calculator, we should get 4.175 times 10 to the minus 4 meters. And in terms of millimeters, SF equals 0.4175 millimeters. So what we've learned from our calculation is that our charge is going to reach to about here. So this is our SF. So our charge is going to move to the right, it's going to slow down, slow down, slow down, it's going to stop as it gets here, it's going to turn around and come on back. So that's the behavior of that charge. We're not asked where it stops, we're asked how close it comes. So we have one more step in our problem, that's to calculate this distance delta S. That's not difficult to do. We know how far this is, we know the plates are separated by 0.5. So our last step is delta S equals D minus SF. So how close it comes is 0.0825 millimeters. Okay, any questions yet?
Yeah, is it practically possible for the charge to go beyond the plates?
Oh, that's a good question. It can't get beyond the plates. It's going to smack into them. Yeah. So had we gotten an answer bigger than 0.5, say we had gotten 0.5, that tells us is we know it reaches, right? So that's our bit of information. Then we would put in our equation, but instead of VF being 0, we would leave VF as a symbol, because we know it's still moving, we just don't know how fast. We put in the rest of our information, and we would solve for VF instead. Yeah. And that's what the next slide is, actually. It's an example like this one, but you find out how fast it's going when we get to the next one. The next thing we're going to do is find the electric potential energy of point charges, but there's no way we can finish it in the next 3 minutes. So we'll quit there. Friday is the test, and then we'll pick back up with this on Monday.
Will there be a lecture?
Friday?
Will there be a lecture Friday?
Friday, no, because we have tests.